So far, we've been talking about single degree of freedom system, but now today we are moving on to slightly different systems, where we be talking of the multiple degrees of freedom systems. Okay, remember the definition for the degree of freedom. In this case, we are talking of how many coordinate system, how many coordinates, or if we just talk of the axis, how many we need to describe the motion or the position of our structure at any given time. Okay, remember the general definition for degree of freedom, where you have tackled in other structural engineering courses, is about the coordinate displacement, or how many components that a body can be able to be described in terms of deformation or displacement. So we talk of the rotation, maybe in 3 directions. We talk of translation in 3 directions. This being the case when you are in Cartesian plane. And that, remember, we narrowed down, or we kind of specified for dynamic system. Now we're just talking about the axis. The axis, the number of coordinate systems are required to describe the motion. All right. So for the single degree of freedom case that we have been talking about, remember we said mass is concentrated at floor level. So basically, we are talking of a single story with a single mass. And therefore, at any one time, you can describe a motion for that mass because it's about the mass, displacement of the mass, or the motion of the mass. We're able to describe using the one horizontal coordinate, okay? And when you talk of the multiple degree of freedom dynamic systems, there are a number of them. You can have what you call the shear buildings, or the frame structures, or even a continuous system. And this being an introductory course, I would just like us to concentrate on shear building, the first one. So we want to see what are these shear buildings. If you look at this is a residential house, and I believe for high-rise building, you have seen this, that and especially where you have the lift core, you find like at a certain area, especially at the middle, the center, we have we have reinforced concrete walls. Okay, so this is what I'm talking about. You have reinforced RC walls for high-rise buildings. This what we call the shear walls. The purpose is to take the lateral loading. Okay, when the structure, if there is a sway, or if there is lateral loading, could it be earthquake, could it be heat loading, or any other lateral force or loading, maybe on this direction, we are saying that the shear walls, the reinforced concrete walls, are able to take that loading, and of course now prevent excessive deformation of our structure. Now, this shear building, we are saying that there is no rotation of horizontal section at the floor level, and therefore deformation is similar to that of cantilever. So what we are saying is that for at the floor level, yeah. So remember now, for multiple degrees of freedom cases, we are talking of multiple story buildings. Okay, so if I can have a 4-story building there, so we are saying at mass is lumped at the floor level. Remember that's what we said, and therefore we assumed that the beam's mass is negligible compared to the mass at the girder level. Okay, and that such that the column only provides what we call the stiffness. Okay, the restoring force to deformation. And we are saying for the shear walls, there is no rotation of horizontal section at the floor level. Okay, so what we are saying is that this part, if this is the floor level here, this part is very rigid, such that the deformation will be like that. I remember we brought something like that, but when you come to the floor level, the deformation, there is no rotation. That is, remember, if you are talking of rotation on the floor level, like when you are talking of the sway in structures, we talk of something like that. If this is our initial structure, okay, and then there is the deformation. We talk of the deformation occurring like that, and then also the girder level floor level deformation occurs, and the same case with the column. But here we are saying there is no deformation on the floor level here. Okay, so basically it's only the columns which are deforming. Now, Now, if we move now, that was just a brief description and also illustration of where you might be finding them when you come to design of high-rise building, especially analysis of lateral forces and or lateral loadings. And the assumption that we make are very similar to what we did generally for single degree of freedom system. Remember this assumption, of course, I remember you saw something like this before, I think in our first lecture. This, our first lecture, which was basically on introduction. I mean, we are describing some of the concepts that we talk about that we use in structural dynamics. So I used as a three-story building, and I was giving the assumption that one, the mass is lambda at the floor level. So basically what I was describing at that time was on multiple degree of freedom systems, okay? And therefore, for the assumption in the previous slide to hold in slide 72, that there is no deformation at the floor, rotation at the floor level, then it means the floor level or the girder level is very rigid, floor slab, very rigid. It's not flexible, okay? And again, we also assume that there are no deformation due to axial force. The axial force, these are the vertical loads, like the dead load of the structure. So this is when we are analyzing, when we are doing the analysis for the shear walls or shear building. So apart from the self weight, of course, but basically what you're saying, we are analyzing for the lateral loading only. Remember, analysis of a structure, you consider different cases, what you call the wholesome design. So in essence, you already have done your typical structural analysis when we consider the dead load, the life load, and all that. Then when you come to design, and you'll find this in next design, I think design 4, when you are doing the seismic design and also the wind loading analysis, you're going to look at the cantilever method and all that. Right? You find like you kind of are not considering vertical loads. Why? Because this is a specific analysis that you are conducting to see the behavior of your structure. It doesn't mean that they are not considered in the overall design of our structure. But for the analysis for like seismicity or for wind loading, then it means what is critical is the lateral loads, and that's what we are analyzing for. Remember, sometimes if we introduce the axial load, the vertical load, which applies some force on the structure downwards, they might be acting as a restoring force. In fact, making you, of course, when you do the design, when you combine them, they provide what you call the economic design. But in this case, we want to see to minimize the analysis cases, the parameters that we need to consider. So we hold some constant. Number two, we want to have a worst case scenario where there are no particle loads applied. Okay, so that's why we are talking of no deformation due to axial force. We are interested in the vertical analysis. I mean, in the lateral loads. Now, look at this. So you have already given the assumptions. And then this is now what we are talking about. You remember, we started with, when you're talking of dynamic system, we started with a real case, a real complex scenario, which is the reality, our structure. And then we move to the simplification of using a physical model or a representation. And then we move to, of course, the dynamic system, right? Now, in this case, you see, we are talking of our building, which was a multi-story, a three-story building. And in this case, there is a lateral force applied at the floor level, because that's our assumption, that those are applied at the floor level, and the mass is concentrated at the floor level. So all the mass for the slab of the beam is M1 for the first floor level, M2, M3 for second and third floor level, respectively. And then, of course, the stiffness of the column at this level, K1, K2, K3. So this is what we are talking about. You see, and be very careful with the head fixity, because the way now this sketching is done here, I believe this man must, whether it's by mistake or he assumed to do this, then it means that this column, this support system here is a pinned joint, right? It's a pinned foundation. That's why you can see even there is rotation at this foundation. But what you are saying, what I wanted to mention is at the floor level, when you come at the floor level, you can see the girder level is very rigid, so there is no deformation. So when you come here, there's no rotation here. Okay, there's no rotation of these girder or the floor level mass. So the displacement at the first floor level is U1, at the second floor level U2, and of course, they should be U3. And now remember, we are describing our motion using displacement, right? So U1, U2, U3. So this tells you that for this case, for 3-story building, then this is a 3 degree of freedom dynamic system when you do the dynamic analysis. For the n degree of freedom, that's we're talking of n stories. Now, remember we talked of representative quorum stiffness. That is, even if this is just one bay that we are taking, but even if our building is subdivided into many bays and the frame that have many bays, we need to have a representative quorum. Of course, remember when we are merging the stiffness for the different quorums, whether they're in parallel, whether they're in series, or whether to have a representative stiffness, so that now we have a single quorum model. And again, we just show the displacement U1, U2, U3. And now to do our mathematics, we use what we call the free body diagrams, such that we can see the mass of the floor before we separate from the mass of the second floor and so on. We want to see which forces are acting on this body, okay? So that you look at this, just like the way we analyzed when we are deriving the fundamental equation of motion. We started by the free body diagram. We see the forces acting when it's in motion. What are the forces acting? So there is the externally applied force, and this is the F1, which might vary with T. If this is a force vibration. If it's a free vibration, of course, now the F1 will be equal to 0. And after that, you consider this was, remember when we had for a single degree of freedom case. Let me just have that first, so that we understand this concept well. So for the single degree of freedom case, so this would be our single story. So a representative physical of the physical system is like that. So our mass is there, and then we have what we call the stiffness K1. Then so we have this stiffness K1. And then we have, so we are considering, because of the mass M, the Albert's principle, the inertial force, which acts in the opposite direction. It's a restoring, it's a restoring force, because, of course, the Newton's second law of motion, the first law is that the body tends to remain in a state of motion or rest, unless compared to blue eyes. So the inertial force always acts in the opposite direction to the motion. So our motion is in that direction because of the externally applied force. So the inertial force, MA, or MAU, here, is operating on is the restoring force. The same case with the stiffness. The restoring force to the stiffness of the column, which is equal to K times the displacement U, again is operating, or it's acting in the opposite direction of the motion. And if there was damping in our system, of course it would be kind of trying to stop our motion. So in essence, if we are just considering for a single degree of freedom case, this part on top will not be there. So a free body diagram will only be having this force, externally applied force, and then the restoring force due to the Albert's principle, and then the restoring due to the stiffness. And of course, if there is damping, the CV would be applying again in the direction of the restoring forces. But now here there's something very interesting, because these systems, or these, let me just delete these, at least this one. So this system is connected. I mean, our structure is connected. The first floor is connected to the second floor by the column. So there is some force. When the second floor mass is moving, it affects, it's like the way we are talking of in finite element methods, where we are talking of node 1 and node 2, we talked of something we refer to as shape function, the n and 1 and n2. Remember, the n1 and n2 are integrated, that at one node, at the node 1, the n2 is 0. The effect is only brought about by the n1. But as you continue between any point 1 and 2, there was the contribution effect of the node 2, because n2 also has some factor there, and n1 has some factor. Until you come to the node 2. The node 2. I'm using this example because, of course, we just came from that lecture in last semester. So it makes you to easily understand. So what we are saying is that at this for this mass M1, there is a contribution of the stiffness in the second floor level. This one in the first floor level. Okay, this is the ground floor level. This is the first floor level. But if you're in like in Japan, they do not talk of ground floor level. They talk of the first floor level, second floor level, like so on and so forth. But that's neither here nor there. So what you're saying is that there is the stiffness of the column because of the connectivity here. There is the force that is transferred to this mass, and it now this for in column one or in mass one, it will not be a restoring force, but it will be an overturning force, right? The force that brings about the motion. So this is it adds to the effect of the externally applied force. Yeah. So K2 which is the net effect of U2 minus U1 because it follows the Hooke's law, the column stiffness. So there's a net effect, the displacement U2 minus U1. So basically it will be slightly less force compared to when if the two bodies were not connected. But if they are not connected, if the M2 mass 2 was separate from mass 1 and this column, column 2 is not connected to this mass M1, then there will be no contribution of the stiffness of the column K2. So in that case, then you can see for when you come to the second mass, the second floor level mass, again this force now because now of the equilibrium, it acts now in the opposite direction. Okay, so this is a matter of equilibrium. This is applying restoring force. In this direction, is applying in the other direction of the applied force. This one is in restoring applied force, and so on and so forth. And then, so you can see in the free body diagram for the mass 1 and mass 2, the stiffness are contributed by 2. We have 2 contributions of stiffness, column 1, column 2. This one, column 2, column 3. Of course, the force 3 is just column 3. But you see, there's a net effect because of this. We have to get the difference between the displacement at the second, that at the second floor level. Okay, so these columns are very, very, these free body diagrams are very, very important because they help you to understand the interaction and relation between the different floor levels, but the concept remains the same. Remember, we say that the equation of motion, the fundamental, whether you're talking of any degree of freedom of the system, this is the fundamental equation of motion, that M times acceleration plus damping times the velocity plus stiffness times displacement is equals to Ft. So all that remains is that we need to, for any system, what we are doing for single degree of freedom system, for multiple degree of freedom system, for continuous system. And when you talk of continuous system, remember now you're not going discrete analysis. So basically you'll be having a lot of partial differential equation in a continuous form. Okay. Now, so what we are just doing is to see for the mass M1, how many forces are there? What is the force? Using the fluid body diagrams, now we can be able to get this force to describe the equation for mass M for level 1, level 2, and level 3. And this is what now follows in the slide that follows here. Okay, this is what follows. So again here, but you might use this or you might just avoid it. It kind of just tries to bring you the picture, the same picture that you had in the single degree of freedom case when we are using the mass spring model. And in this case, we were looking at a mass to represent the mass of the system. Then the column stiffness is represented by the stiffness of the spring. And then we introduced what some old books usually call the dashboards. And in this case, for now, if you look at this system, we are not showing the damping. The damping is not shown, just for clarity, but you can introduce it here. Remember, the up to this part, of course, is what we had for a single degree of freedom system. Okay, so you can have for multiple degrees, so multi-mass spring model, of course, for multiple degree of freedom case. And you see now you need to have coordinate U1, U2, and U3, or X1, X2, X3 to describe the motion at each floor level. Remember, why we are not using a single coordinate or a single is not enough is because if you look at this, the displacement of our structure, right? U1 is different from U2, it's different from U3. And things we start becoming very interesting because once the motion structure has been set in motion, this is the fast, they go in the fast direction, right? Then when it's returning, because you know it's oscillation, it's going back, these masses will not come back in the same manner, just the same way you swing the rope. So you find this to be in that direction, maybe this could be in this direction, like that. When it goes to the third, I didn't want to use that term at this stage, but we talk of the mode. So the third, we may find like this one is left on this side, maybe this one and this part on this side. So in essence, why that's what we are saying. There will come a time that U1 is positive, U2 is negative, depending on which mode we are in. Okay. And that's why we are saying we need three, at each level, we need a separate coordinate to describe the position of the struct. That's why we're talking of 3 degree of freedom system, or n degree of freedom system for n levels of stories. Right? So now with the degree of freedom, I mean with our matrix mass spring model and our free body diagram, the same thing, of course, you are separating this to see the forces. Remember the free body diagrams, there's a separated body that shows all the forces acting on that element. Okay, all the internal forces and external forces acting on that element or that body. So that's what we are doing here. We are separating this body like this, so that you can see all the forces that are acting in the restoring manner, or they're acting opposite to the applied force. So you have the force 1, you apply this applied force. We have the stiffness due to column 2. Now it applies in the direction of the applied force. It's acting on the direction of the applied force. The same case that you have done in the previous slide. But now we have the restoring force due to inertia and the stiffness of column 1. And same case you can do for second floor level mass. And you see for second floor level mass, we have the stiffness contribution because of the K2 and the K3. And same case to M3. So it's not very complex. Maybe you find them being put together. Being put together, like you find it's crowded, but it's for your understanding to see that these things are interrelated. Because you see this like called an action and a reaction. So these like two, they provide the equilibrium how to be maintained at that location. Okay. So what you just need to do now is move ahead and now develop or just substitute the values in our fundamental equation of motion. And in our fundamental equation of motion, remember this is 3.1. So we are saying this free vibration, free and undamped. So that is why there is no damping. And now F1 will become 0. So if we move now to the equation of motion, the F1, the external force, okay, remember it's about m times acceleration plus c times velocity plus k times displacement is equals to ft. So basically we are saying this is equals to 0, free and damped, this is equals to 0. So we are just left with, we will just be left with this part, okay? So mu plus ku is equals to 0, okay? It's equals to 0. And if you remember very well, is that when we are talking of this type of a system, we talked of the equation when it's when there was no damping and this was free vibration, it simplified to homogeneous linear second order differential equation. Which solution, of course, you remember you see the typical solution is u is equals to a cos omega t. Okay. So now if you look at this equation, so you're saying for the first body, we have m1 u1 plus k1 u1. Okay. What are the forces acting on the first free body diagram? Yeah. What are the forces that are acting on this? So you see, it's about you add this, the restoring forces, m1 a1 plus k1 u1. Of course, this now f1 is equal to 0. And then this one, it will be acting in the opposite direction. That's why it's minus k2 u2 minus u1. That's why you have this m1 a1 plus k1 u1 minus k2 u2 minus u1 minus f1 t is equals to 0. Okay. And then, what else do we have here? Then, of course, this F1 and F2 and F3, all these should be equal to 0 because these are externally applied forces, which we are saying there's a free vibration. So maybe you can help me correct that. But you wanted to show you that this equation here, the single degree of freedom case that we are considering, is the same. Of course, equation 87 is written like that. But in that case now, we are talking of the matrix, the mass. We'll have this in matrix form. So when we are talking about MDoF functions, we are saying we aren't necessarily talking about forces in more than one axis, but rather forces acting on multiple bodies in a system. Forces in more than one axis. I don't want to be trivial, but remember, even when we talk of degree of freedom, in essence, we talk of the displacement, not in force. We describe degree of freedom in terms of displacement, not forces. But I will hold it for now and assume what you are referring to is that for the dynamic system is that we are talking of where you have used force, talk of the displacement. So is a displacement in different, in multiple bodies. Displacement component for different masses or bodies, M1, M2, M3, depending the flow level. Okay, so I prefer you use the displacement instead of forces because that the description of the degree of freedom is about the displacement component. Okay, so what we are saying is that our equation, the only difference that now this mass and the acceleration, stiffness, and the displacement and the forces, all these are they are in matrix form. Yeah, because if you look at this equation, we have prepared this equation for this is the first flow level, second flow level, that flow level. We want to write the compact equation, so we can write in matrix form. Okay, like M. Then this is a rectangular matrix. In a rectangular matrix, and you see, if you write this equation in matrix form, of course, this is very simple for you. Just bring the rectangle together, the M and the K. You see, you bring the K's and K1, K2 together and K3. And then, of course, the force vector F1, F2, F3. So you see, M is the rectangular matrix, but the K is of and K, but the displacement U and the velocity and the acceleration and the forces, these are column vectors. And that's why you have to be very careful with the usage of them, the braces and the square brackets. Okay, so we are back to matrices. Now you know what happens. To solve this, we need to use the principle that you learned in matrices. But you are lucky that in last semester, suppose when we are in finite element analysis, you refreshed your memory in dealing with matrices. So you can see even in this case, when you come to multiple, when n is greater, when it's continuing increasing, of course, our matrix now becomes bigger. That handling it manually or by hand may become very tedious. So that's why you might limit ourselves maybe to just two or three stories. Maybe for an example, possibly just two stories. But for our description here, we might even go to 3 stories so that you can appreciate this derivation for different levels. Okay. So we have already now derived our equation for the multiple degree, for the multiple degree of freedom undamped systems. And we have seen the force vector and the displacement vector. And just going ahead now solving these equations. We are saying, remember, from equation, if you can remember, was it equation 8? I believe it must have been equation 8, if my memory serves me right. No, 6, 7, and 8. Single degree of freedom case. And we said one of the typical solution was that U for a linear, homogeneous, ordinary second order differential equation is that this is a typical solution, A cos omega T, right? So in a similar manner, of course, now there was no, we are talking about free vibration. So the F component. So why we had maintained the component F is that you can see the vector, the force vector here, F1, F2, F3. But we are saying it's free vibration. So the force F component, the force vector is 0, no externally applied force. So the motion is just about brought about by the initial conditions. right? Now, so I was saying in a similar manner, we can say a typical solution is that U is equals to A sine omega t, of course, minus alpha. These are what we call the phase angles. And or in the vector form, of course, because the displacement ui is the displacement at a certain level, maybe u1 or u2 or u5, un. So that's why we know that the u will be a vector, of course, a displacement vector for the different flow levels or the different degrees of freedom. Remember, it's like flow levels here is akin to the degree of freedom. Okay. And then A, which is the displacement or the amplitude of our motion, the response at each individual flow level. Yeah, where AI is the amplitude of motion of the ith coordinate. And then note that there's a number of degree of freedom. So of course, when you get the solution, which is equation 91, what you do is substitute it in your problem. Yeah. So this is a typical solution because you want to obtain what are these now constants. And then you factor out sine omega t to get the eigen value problem. If you can recall, even after equation 6-7, we came to what we are calling the characteristic equation. Huh? And this, I don't know which course you studied this, which math unit you learned about the eigenvalue problems, the characteristic equations, and all that. So when you are substituting, of course, the solution to the problem, and then you factor out the sine omega t, you are left. This is the sine omega t is the oscillatory part, is our motion part. Yeah, it's one that works about the oscillation. So we factor out this component, and we factor out sine omega t to be left with this equation 92, which now we refer to as the eigenvalue problem. And because of course you studied this much in a previous math problem, you might not delve so much into this eigenvalue problem, but you should know about them. And for those people who are inquisitive enough, when you did your modeling in Abacus, if you went to what we call the message file, is it the message file or the report file? You open inside there. If there was an error, if you're doing analysis and find an error, most of the times you might, it's probable that when you try to analyze or to see that error, you might see the issue of negative eigenvalues and so on and so forth. Because when this equation is being solved inside there, and then because of maybe how you have done your modeling, maybe you have over-constrained your model, and then you find unrealistic values, some of these components, what you call the eigenvalue, becoming negative or unrealistic. So we need now to analyze. Basically, what we do in our analysis for multiple degree of freedom, we want to see what is the natural frequency and something we call them the mode shift. Now, why frequency is important is because in actual structure, we try to avoid something we call resonance. Okay? Because remember we said when resonance occurs, when the forcing function, when the frequency of the forcing function becomes the same as the frequency of our system, right? Then the amplitude becomes too big. So collapse might be imminent, right? So we are trying to analyze our structure to know what is the frequency of our structure and what is the frequency of the forcing function so that we can assure the safety of our structure, or we can try to mitigate against. Because we see sometimes some of these forces, you might not counter, you cannot provide completely, you cannot design completely against some of these destructive forces, like earthquake. Because again, your design might become very uneconomical. And number two, some of them are unpredictable because like the earthquake, the one that we experienced last year or last time that it was recorded is different from the one that might come. Okay. If it's below what was designed for, then well and good. If it's higher, what we try to do is we design our structure against a certain set threshold. And again, what we also do is we try to look at systems, and this is what when we call of damping, for example, in bridges, because bridges carry a lot of dynamic load because of the big tracks. So the issue of the bearing and also the dampers. yeah, so that they can try to absorb as much energy as possible of the dynamic load. Okay. So so you're saying for non-trivial solution, remember the eigenvalue problem. The eigenvalue problem. So it's like this: K and omega squared M. Remember, for you to obtain this, of course, you have to substitute this here and then work out, simplify the equation. And what you're saying is that A is the amplitude of the motion. So what you are saying, when you say for non-trivial, it means it has to be for a rule that you need to apply a rule that applies across both throughout the vibration, throughout the vibration history of our structure. So in this case, we are saying if at one point A can be equal to 0 at the start, or at another point, maybe at rest when it goes to and fro, sometimes it could be 0. But we are saying for non-trivial, so that at all times this situation holds true, because we are saying this component times A, the amplitude is equal to 0. So at all, this cannot be equal to 0 at all times. So it means this component, for non-trivial solution, this component has to be equal to 0. So for non-trivial solution of the eigenvalue problem, this component will be the what we call the determinant of that equation have to be equal to 0. So of course, when we expand equation that 3, we get what we call the characteristic equation, which is a polynomial of n degrees in omega. Remember, the omega is the angular frequency of our system. The small omega, we say that this is the angular frequency of the structural system, dynamic system. But the capital omega, this was the frequency of the forcing function, if the forcing function is sinusoidal in nature. Okay. And now the solution of these omegas are the eigenvalues, the one I was talking about. And of course, we'll have depending on the number of degrees of freedom, we'll have a number of solutions. And the lowest value of the omega squared is called the fundamental frequency. And remember why we are saying the expansion gives a polynomial of n degrees in omega squared. It's like if you have this equation, just to simplify the matter, if you have an equation like omega raised to power 4 plus 2 omega squared plus or this is equal to 0. So this one I can write it to omega squared plus 2 omega squared is equal to 0. It's like this omega squared act as one unit. This is like a squared plus 2a is equal to 0. And that's why we are saying our polynomial will be expressed in terms of these terms, omega squared, not just omega. Okay. And the lowest of it, we are calling it the fundamental frequency of our system. So each of these values that you obtain, there is a lot of write-up here that you need to just read, and it's very summarized. It's very summarized. If you need more expansion on this or explanation, of course, the book that I have derived from, the one that the reference number 1, it talks about much about what are these. In details, the theory on these frequencies. So you're saying now the solution of this, of course, will give you this omega squared, which are the frequencies. And if you substitute the solution, which is omega squared, which you have already obtained, into our eigenvalue problem, which was given in equation 92, yeah, you substitute this value here. The equation 92, you get a certain set of amplitude vector. Okay, you get an, of course, the vector for first floor level, second floor level, up to nth floor level, the amplitude. And each frequency, of course, will have its own characteristic discrete shape of the degree of freedom called the mode shape. So that's kind of the theory or the description here we are giving us to define what we are calling the mode shape. And remember, when I was describing in the previous maybe 2 slides, I was saying I don't want to go ahead of myself because I wanted to describe something about this, the term mode shape. So the mode of vibration. So when the vibration is maybe the first mode, like, it goes and comes back. It goes to and floor, to and floor, to and floor. So the first mode, something like that. Something like that, like that. So it's first mode. And for each levels, we have the amplitude maximum displacement to be A1, maximum displacement A2, and A3. Remember, U1, U2, U3, U1 varies. Maybe at different times U varies, but we are saying U maximum is equal to A. Okay, it's maximum amplitude. And now this is the first mode. So the second mode, let's go back. So we are saying this could be on this direction, and this is given by calculation of these A's. If A, you calculate the value of A and you get is negative, then if you started on this direction, this to be the positive direction, then it means the negative direction is on this side. So if A1 is negative, then the mode shift. Now this is on this side. You get A2 is positive, then it means this comes like this, then it goes like this. Then if you get A3 is positive, then it's like this. And depending with the mass, with the magnitude, if A3 is greater than A2, of course, this one we should have used maybe a different, we are talking of the second mode, could be something like that. So what will determine the mode shape of our structure is the value A1, both the sign and the magnitude, okay? So what left with us is we want to sketch. We get the frequency, fundamental frequency, and also we want to sketch, understand the mode shape of our structure. So in free vibration problem, of course, the amplitude value of the value of the amplitude is unknown. Of course, these values of A1, A2 for free vibration might be unknown. Therefore, we express them relatively to one another. Okay, we express A1 relative to the adjacent floor level. So it's kind of, you might find like A1 is 0.8 of A2. So this is just what this last statement means, but we are going to see in an example that follows. Well, that's an explanation, and I've tried to avoid today as much as calculation and derivation as possible. But we are going to see the application when we come to a problem. Application is very, very easy. So let's look at this very simple example. We are saying this is a two-story building. I've got very steep floor slabs, of course, now so that there will be no rotation at the floor level. And you are given that the natural frequency, you have to calculate the natural frequency and mode shift. You're given the flexural rigidity of the column. Yeah? So this Young's modulus multiplied by the moment of inertia. You're already given that. So you look at this, okay, you're given this is a problem. The mass is given at the floor level 1 is 5 tons, second floor is 3 tons. The height, 3 meters. So it's a typical house. Yeah. And then the displacement U1 and U2. So we want to know what is the natural frequency, the lowest frequency, and the mode shift. Of course, two-story building, 2 degrees of freedom. We have a typical model for the shear frame. There's no damping, so just the stiffness for the column K1 and K2, the displacement U1, and the mass, of course, M1 and M2. Now, we need to get, remember, these are 2 columns for each floor level, so we need to get the equivalent. So this point is fixed, the bottom is fixed. Now, because of this rigidity here, it's like our column behaves like it's sliding. So it's like this. Yeah, it's like it's sliding here, sliding. So basically, it's kind of, you can assume it's like we have rollers on this top. So that when you have a fixed head and a roller, it helps you to know the equation, the appropriate equation that you're going to use when you want to calculate the equivalent column stiffness. And you're saying K1 is equal to K2. So to get the K for the first floor level, which is 2, so of course they are in parallel, you just need to add them. 12 EI of L cube, L which is H, of course, the height we get what is the stiffness of the column. Now for a 2 degree of freedom system, so we have the matrix for the mass, those M1, M2. Remember, this matrix is very easy to recall because we only have the component in the main diagonal, and any other values or the element in the other diagonal, in the other cell is equal to 0. Same case with the stiffness K, K1, K2, minus K2 like that. Then, and you have to be very careful because if you look at this, it's an equation that collapsed this form. This is just derive. You can derive from, if you say derive from basic principle, not here carefully. If you say derive from basic principle, right? If you're showing from basic principle, it means we need to get this equation. We need to get the shear, the body. Whether you want to use this, whether you prefer to use this form or this form, multi-mass spring model, we need to see the forces acting so that we can see you deriving this equation that you can be able to condense. And of course, for examination purposes, somebody may want to see whether you can be able to derive this. So for 2 levels, for 2 degrees of freedom, 2 stories, then it means, of course, when U3 disappears, the equation is very simple, which can be worked out by harder. So that you don't just come and jump to this level. But of course, if you're not told to derive from first principle, then no need to come from that. Okay. So you see now there's no M3, and then there is no, of course, K3 here. Then another thing I was saying, you have to be very careful because I know you have just come from the course finite element method, where if you look carefully, where there was sharing of node, if it was K1, K2, and K3, you would have found that where we have K2, K3, at the K2, K3 is where there is sharing of node. But you see here, even at the first element, we have K1 plus K2, because this we are deriving from what? From free body diagram. It's slightly different. This is what I want to say. The K, the combined stiffness. If it was for the just 2 nodes for the infinite element analysis, we just have K1 minus K1 minus K1, K1. No, K1, like that, combined K1. The second part is what we are having K1 plus K2. Then we have K2 here at the bottom. So don't confuse that because they almost look similar. These are different derivation. Okay, and then of course the characteristic equation. We already know the characteristic equation is from when we get the dynamic of the eigenvalue problem. When you get the determinant of the eigenvalue problem, okay, the eigenvalue problem, which is this component, and of course there was an A, we get the determinant of this part. That's when we obtain the characteristic equation. So these vertical lines here means the determinant, for those who might have forgotten. So in essence now, what you just need to do is that you substitute this K, look at K. K is all this, and M is all this. So in matrix form, then this is, we have opened up, okay, out to be able to express this an equation, a linear equation. And now you can substitute what is K1, what is K2, and what is, of course, the combined K. So you just need to solve this equation, and you obtain omega. Remember the frequency said you obtain it in forms of omega squared. So you see here we have omega raised to power 4, omega squared. So you can write this omega squared, so that you can have a quadratic equation with 2 roots. N is 1 and 2, of course, the number of degree of freedom. So root 1, 425, root 2 is 25/8. And therefore, the fundamental frequency, of course, the square root of that, we have 20.6 and 50.1, of course, ignoring the negative. No? And the natural frequency. Now, this was circular. This is a natural frequency because it's angular frequency divided by 2 pi. We get all that. This is in hertz, this is in hertz per second. So you have to obtain what is the frequency of what structure. And this becomes very important. At this stage, you just stop there. But this becomes very important because when you come to forced vibration, you're going to compare this with the frequency of the forcing function to see whether there is resonance. Okay, because if the resonance occurs, and we know our structure is the structure is susceptible to failure as a result of the resonance or the very high amplitude of our motion occurring. Remember the material that we are using, even if it's steel, even if it's concrete, there is a maximum allowable deformation. Of course, even from the code, like when we talk of L over maybe L over D. You are given for a slab that it should not exceed this value. For a building, you say this should not exceed a certain value. Okay. Otherwise, after that, now it's a usability limit state. Even if the structure may not collapse in ultimate limit state, then in terms of serviceability, the structure may have, or your design may have failed. Okay. Wow. I thought this lecture will just take 1 hour. Okay. Now the mode shape. We want to see the mode shape for this structure. Yeah. The mode of vibration, not the shape for vibration. So you see from the equation, yeah, from our eigenvalue problem, equation 92. First, we need to solve for what is this part. We need to solve for this part. Okay. And then we also need to solve for when the whole of this is equal to 0. So that you can get for the amplitude AN. Then we form phi n. Phi n, of course, we say this. For the free vibration, we express it, the displacement or the amplitude as a ratio of 1 and 2, or 1, 2, and 3. Yeah. We can't get them in absolute terms. So for 2 degrees of freedom case, of course, yeah, we just need to see En, or E1. So K, you substitute the value. Remember the matrix K is here. Then omega squared M, of course, you have M1, M2 like that. Or you simplify that, it works out like this. So En is like that. So remember, E is just a representation of this part. I hope you are following also using your note. That's why I'm moving slightly faster. Then remember now, you just need to substitute the values of omega squared. When the omega, because you have the omega n squared varies, we had the omega n squared have 2 values, 425 and 2508. So when it's 425, you substitute what E1, you substitute that value, and you are going to get that E1 is like this. Hence, remember the first part was to get what is E, and then so for EA is equal to 0. Or you can just come down and say you are solving for what EA is equal to 0. Or you are just solving this equation by substituting this here. And of course, A, because it's 2 degrees of freedom, you have A1 and A2. So from this, we are saying we are going to get A1. Of course, A now is A11, A21, right? And this is a maximum displacement for level 1 due to deformation at floor level 1. Displacement at floor level 1 due to deformation in level 2. Because we said the columns 1 and 2 are interconnected. So A11 is equal to, of course, once you solve this, you get that answer. Or this is what you're saying, you can express this as a ratio that the phi 1, of course, the deformation component, you just need to divide by to make one unity, and then the other one, of course, like that. And I think something that's missing here. We could be having it one. So forget about for now. For now, I believe you can just forget about this one, because if you just come to this part, we are well and good. So similarly, for you substitute the value of omega squared for 2 when it's 25 away, you're going to get this. You're going to get this answer A12, the second mode equals to minus 0.8118. So what does this tell you? So you sketch the 2 frequencies and the associated mode shape. You're saying for the first mode, when F is 3.281, of course, when the first frequency. So you're saying the first case here, we obtain A11 to be, both of them are positive. So A11 is 0.6818, or if you simplify this, you find the A1, A11 is a fraction of A21. Therefore, you're saying A11, so you see U1 will be a fraction, 0.681 of U. Of course, remember A is the maximum displacement, it's maximum U. So in that case, you apply, this is 0.681, this would be 1. So again, the second mode here, mode when F is 7.97 of the second frequency. So you're saying now you have the negative. So this tells you now our motion have gone the other side, but the mass at the second flow level is still on the positive. If we assume this to be the x direction, if we assume this to be the positive direction or the positive u direction, so for the second mode, we are saying the mass at the second flow level is still on the positive direction based on the calculated values here. So the sign is very important. And the first level is I've already come to this direction, to the negative direction. So things start becoming interesting when we go to the third and the fourth level because the shape continue changing. Okay, and that was what this question required us to do. Yeah, because we are required to calculate the natural frequency and the mode shift. Remember, this becomes very important when you are doing the seismic analysis. You incorporate them in your design also, because the design code that you use there have some specification. That's the maximum amplitude at either of the modes. So that's why you may see for the analysis, it's kind of we are adding it here. So because the design now, you take it from here to use this result now in the design of your structure, so that you can now start deciding what type of material do I need to use. Is concrete columns adequate? Do I need to use steel columns? If the deformation that is anticipated is very high. Okay, so and that's it for that simple problem. Okay. If you look at of course, next we have given just a simple two examples that you can look at. And example 2 is very interesting. You may need to look at it carefully because you have multiple base-to base, and then you need to coalesce them. You'll be able to obtain the representative physical column representation. Then you get the figure diagram, and then you do your analysis. Yeah. The first one, I believe it's the same, very similar to what we have looked at in the previous example. So just you can do your practice with it. Of course, next time we look when there is forcing vibration. We'd like to stop there for today so that you can digest what you have. And also for the remaining time, you can also be doing your practice. Then allow me to edit there. And wish you well in your other studies. In case you have any question on these or other videos, you can always leave it in the comment section on each video, and then we can look at it along. So I believe you're okay. Then we edit there, and wish you a good day.